when we started this out, obviously things morphed throughout the, this has been a couple years now. And in terms of, refining and honing in on different ideas, but some of the primary objectives really to, talk about this idea of the ICT and facility synergy. I mean, that's really kind of a trite and often overused term, but I think it's interesting because it's kind of a metaphor for what liquid cooling is, where we're closing that gap between the facilities and the IT. So this is we're converging inside of the computers. I think it's an interesting idea. Which, I mean, the projects that I've been involved in using this have really had a really close relationship between the end user, the thermal engineer, the IT manager, and then on the facility side to understand what's required for this type of system. So I've always been a big proponent of that, but I think this kind of takes it to the next level. The other part of this, which is important from a energy standpoint, is understanding the climate impacts, meaning location. This again is not rocket science. I mean, we hear all the time about big data center developers and users going to either cold or very mild locations. But what was important in this tool is to kind of have the ability to demonstrate that and do different options for developing energy use. So that's kind of a big part of the tool, which I'll talk about. And then finally, the developing the capital expenditure and the operational expense related to energy and maintenance to ultimately do this TCO. So that's really kind of the big picture. If you bear with me for 1 minute, I will. Okay. So this is a spreadsheet-based tool, to keep it simple and making it able to be used on different platforms. We wanted to just keep it in this form for now. But the way that this is organized is each kind of thought in terms of an input or an output is a separate sheet. And I'll just talk a little bit about the structure of the tool, because I think that's important from an understanding how it puts together and how the information flows. So what we're looking at right now is kind of an overview or a description of the different elements of the tool. And there's really 6 main worksheets. One is this location, where you see input, but that's obviously an input sheet versus an output sheet, just to kind of keep the organization clear. So the first one is really starting at for in the realm that we're dealing with here in terms of this kind of high level concept, developing a concept about the TCO. What is the location and what are the impacts of that location from temperature, humidity, the ability to do economization, et cetera. So there's, obviously I'll walk through all these. That's kind of the first thought. The second is, okay, so if we're talking about reducing energy costs, you have a couple different aspects of that. One is the servers themselves, and in this release, we're not talking about reduction in the servers themselves. We're talking about the facilities end of it, the power and cooling, and there's some thoughts and some work that's being done right now on that end of it. The cost side of the energy for the servers, but at least the thermal reduction and how that impacts the cooling is already here. It's just not that specifically the electricity for the servers. The reduction in electricity from using standard servers with fans. So the next is an output. We start, and you can see this is pretty succinct. It's a pretty to the direct. There's not 1,000 different input fields, and I'll show you why. The next sheet is an output sheet, which really talks about the data center design itself, meaning based on the inputs, what are the parameters of the data center in terms of the size of the data center, watts per square foot, square footage of infrastructure spaces versus, machine room space, and that all plays into the capital cost. Okay, number 4 is the energy output. This is where we're depicting the energy use of that particular system that's been described through the input parameters. And just keeping it simple again, breaking it down into the major cooling components, and as opposed to having many different, the building envelope and a number of other things that, while very important, are not really important for this analysis. So it keeps it simple, and it gives us the ability to do some comparison of different options. First cost, and just what it says, after we get the parameters of the data center through, that's in the third output sheet. Once we have those, we can start to develop at a high level. Again, you'll hear me use that phrase, high level, based on kind of industry standard parameters. First cost of the power or the cooling systems and the building itself from a square footage standpoint. And then the last piece is kind of the really what this is all about, is the total cost of ownership. And what this allows us to do is take the annual energy cost and the capital cost or first cost, and run some economic analyses to determine which option seems to be the best from a TCO. So that is really kind of the high level overview of what we're getting at in this tool. The next sheet, I'm not going to read through this or go through it in any detail. These are just a bunch of different panels that talk about some of the concepts that are built into the worksheet. So if you wanted to understand which data center systems are modeled, or which how the space is computed in terms of the data center size, there's just it kind of touches on to give you some idea on how that's put together. This is not meant to be a very detailed kind of appendix on how the thing is developed, but rather just kind of a snapshot. And I need to mention before I start here in this input is one of the things, and any of you that have done energy modeling or any kind of detailed analyses know that there's this this struggle between very detailed data and not enough detailed data. So if we make the inputs and the outputs so, say, complex, the end user may not, certain end users may not want to use the tool because it's too complicated. Versus on the other end of the spectrum, if it's too easy, if there's not enough input, anybody can use it, but it's not as accurate, or it doesn't dive as deep. So that's always a struggle in this type of analysis tool. So, we were hoping that we hit that kind of midpoint in balancing it. But I would say, if anything, it errs on the being a little more straightforward side in terms of data input. So anyway, I'm going to go through these fairly quickly because I think when you look at it, some of it is pretty easy to understand. So anyway, the first sheet here, it's very simple. One input, it's like what is the overall location of the facility, and what is the different parameters. So like here, I just have specific reason I have Detroit up here. And what this gives us is built into the database is monthly design, dry bulb, wet bulb, basic parameters of the monthly temperatures. some of the climate maximum and minimum. This is all the ASHRAE data, by the way, and then the different climate zones and what currently ASHRAE is talking about in terms of the allowed basic the allowed energy of the mechanical system. I won't get into the detail on that, but it's usable for obviously for this tool, but it's also, I like to think you can use this for other things as well. We have about, I forget, 3,000 different locations worldwide, so it's a good, easy snapshot. It doesn't get into hourly data. It's just purely monthly data for the purposes of this. And then you have some outputs from the bar chart here and the radar graph in terms of the monthly energy, or sorry, temperature changes throughout the month by month. So anyway, that's really the first sheet. So I mean, there's literally one input on this sheet. That's the drop down here. Okay, second. Okay, so this is where we get into more relatively detailed parameters. Okay, so in this sheet, basically wherever there's a gray box, that is an input of depending on what the different category is. So the electricity cost, and these are all user defined. You can put in whatever you want. The maintenance cost as a percentage, the discount rate, which is applying to the financial analysis, and then a rate of energy increase. So it's very kind of like the minimum amount of data to do the calculations in terms of energy costs and maintenance costs. The overall data center power, this really drives the whole energy use analysis based on the what is the overall power that's required for the IT equipment. These next two I'll spend a second on, the air-cooled and the water-cooled. Now what this means is we have the assumption throughout this whole spreadsheet is that we have in the data center, we will have both air-cooled, meaning traditional servers, and water-cooled, meaning what we talked about earlier, the directed chip cooling. And you can, if you don't want any air-cooled, you can zero the % out and make it all water-cooled. But the idea here is that, especially in retrofit applications, there's probably going to be, or most likely going to be, air-cooled equipment. So to be able to model that again at a high level and assign a percentage of number of cabinets, then that allows the end user to say, well, if we ended up replacing 60% of the cabinets with water-cooled versus 30%, what would be that difference? So it gives us kind of numbers to start, like a sandbox, how we want to take these numbers and how we want to apply them. But so that's what this is, and then we can apply a kilowatt per cabinet to each one of those. So that determines the overall mix of water-cooled and air-cooled equipment. Now on the infrastructure side, what we have right now are it mirrors it, where we have what I'm calling a traditional cooling system and a liquid cooling system. So the traditional cooling system is kind of what it means. It's the water-cooled chiller with economizer, or in this case air-cooled DX. Now this is an area. This is going to be one of these areas I'll say. Right now, there's just a couple in here, and there's already, many others have been developed. We want to keep it simple for this first release, but right now we have probably the two most common systems, air-cooled and then a water-cooled chiller. Generally, I know there's air-cooled chillers, etc. So that's to come yet, but at least for now we can start to use these as the basic parameters. Air-cooled system data. What this does is allows, and this is a big part of the energy consumption again, allows the end user to say, well, what is the maximum supply temperature in a in a legacy or not a legacy, in a new air-cooled data center? It could be as low as 55. I don't think that's the greatest idea, but or as high as 70. So we can change the parameters in here and make it what we think, or it should be, or what it is now, or maybe even what it should be through this analysis. Here, this is just kind of a reference thing. This doesn't really change any input. This is just simply ASHRAE air temperature class. So if you're thinking, if the end user is saying, well, I'm not sure what my temperature should be, maybe I'll use ASHRAE, whatever. So you can say, okay, an A2 temperature class will be a 95-degree dry bulb temperature. So it allows the user then to put back in the input the temperature of what that is. So it's more of a reference thing, but since sometimes we talk a lot about how the ASHRAE classes should be applied, I think that was an important little thing just to have in there. Going on to the liquid cooling system, it's the same basic kind of idea as the traditional, where we have a few different, like right now, I have a water-cooled cabinet in there. I'll talk a little bit about that. That's not the water-cooled computers, but for comparison's sake, we can do that. But really, the direct chip and the dry disconnect liquid cooling, which they have different efficiencies. There's different amounts of convective heat from them, so we can look at. I mean, they're subtle, but they can be big enough that they can make an impact on your annual energy costs. So anyway, this is again some other areas we can put more things in. So the water cooled system data, what is the temperature of the water? Here I just have 85. That's I'm not sure what it would be. It could be whatever. Up to over 100 degrees. So like again, here's the ASHRAE water temperature classes. That'll say if you have a W2, it's going to be about a 81 degree. Everything's in Fahrenheit, by the way. I should mention that. That's another thing that we're working on is to have dual units on this. But to keep it simple in the first release, everything's in Fahrenheit. Anyway, the ASHRAE water temperature class, and the user can put in, if they want, whatever those numbers might be. So this is really the two things I just described are the extent of the inputs. So when you start to look at the output, you can figure out how that output is influenced by these two sheets to a certain degree. Okay, so now to the output. These will take quicker. I won't go through in these as much detail. But this sheet forward and the remaining sheets, there's nothing to input. There's no user input. But what this is telling us is, and some of this is just summarizing and parroting back. What is the total load, the number of cabinets, et cetera. What is the quantity of water-cooled cabinets, et cetera. Here's where we get into the data center facility summary, where now this is based on, some of the calculations are based on, kind of industry standard, especially when we talk about square foot per cabinet. Now that's going to include, clearance in front and back, walkways. It's going to include main aisles. It's going to include space for mechanical, electrical equipment. It's a broad assumption on how that's put together. We're not getting into the level of, well, if we have a mechanical gallery and we can take all that out. We're not getting into that level. We're doing a comparison type scenario. But anyway, this will tell you the data center size, the infrastructure size, depending on the type of system, the cooling load for the data center only, and the infrastructure cooling load, and then the total cooling load. So these are all informational kind of, gut check kind of, see if it looks okay kind of thing, so we're going in the right direction. When we get to this side, the air-cooled system data, it tells us the percent, the quantity. We've seen all that before. The area. So this is an assumption. So like a typical cabinet is going to have, much less footprint than that. But this is square feet, 79 square feet per cabinet. But when you do the math and you look at all the clearances required, it's much higher than that. But this is something that in the future we can put a toggle on to make it less or greater. and then the rest of the power densities, square footage, total CFM. So these numbers are used in the calculation, but I wanted to bring these out up in front so the user can get an idea of what all of these are and how they compare. So you can say based on this mix of air-cooled and water-cooled system, you have this much square feet for the air-cooled, this much square feet for the water-cooled, you know, and kind of walking through it that way, so you get an idea of what the two systems, and back to the input, if you wanted to zero out the air-cooled, you could do that and just have the water-cooled if you're not interested in that comparison. Okay, so this is the very straightforward, very simple energy consumption by system type. So the first one, kind of keeping the theme going here. This is the air-cooled system on the far left, and what the energy is based on in this case, it's 50% of the total cooling capacity. It's the liquid cooling system energy use based on the temperatures and everything that we put in the input. And then here's if you want to say what's the total of those two, this is the total. And if we're just looking at direct water cooled, again, this is zero out the air cooled, and then the total will be equal to the liquid cooling energy. And compressors, what these abbreviations are, compressors for the system. Fan, this is all broad collective fan kilowatt hour pump, and heat rejection. So there's a number of different components that will add up ultimately to the energy use. There's probably a lot of you going, wait, where did you get that from? How does that work? But we could talk about that later. And frankly, part of the release of this is to get feedback. I mean, this has gone through a pretty exhaustive review internally with the green grid, but once we get this out into the field, I'm sure we're going to get a lot of feedback, and I'm not going to claim to have everything 100% right here. We want to make sure that this is usable. That's the whole point of this, not to just develop something that looks fun. So here's the first cost, and this is another area that probably is going to get further detail. The way that the systems are modeled, the air-cooled and the water-cooled systems are modeled, we're using a cost per ton of cooling. These are catch-all numbers, so like a chilled water plant of $1,500, a ton, piping $750, chilled water or condenser water system $1,000, and then we're taking the tonnage basically and applying it to those numbers to come up with the cost. They're very high level, based on a number of different built projects, going back, kind of doing a check of what they end up being. And I'll tell you, every project is radically different. It ends up being very similar project, but costs radically different because of area of the country or the contractor's abilities or material availability. There's so many different factors. I won't go on anymore on that. But my point is that we're able to put in these numbers and to come up with, kind of a comparative numbers for the air-cooled and the water-cooled system. So at the end here, we have air-cooled and water-cooled. These are just two systems that are in there right now. They're the same. So we find out that, in this case, the water-cooled is, whatever, $200,000 less in first cost. It's in this particular analysis. So this is where, in the future we may have this, where the user could modify this to their own taste. Just and keep the structure of the analysis intact, but we'll look at that when the time's right, after we start getting some comments. And then the last sheet, this is the TCO. So we're doing a net present value here. We could do simple payback. I mean, there's different methods of financial, and I'm not an accountant or a CPA. I took my engineering economics, and I know this pretty well, but I'm not going to claim, when we start getting into the tax depreciation and all that, that's not what this is about. This is about a real straightforward analysis where we have a first cost, we have, annual energy costs and maintenance costs, and then applying, escalating each year by that factor we saw early on in the escalation factor, and then the final value, which is lower, is better. So in this case, again, I just plugged in some numbers, so if there's probably some things that may or may not be correct. But in this case, I mean, there's a huge difference between the air-cooled system and the liquid cooling system. And this, I'm not here to promote, how or which is better or whatever. That's not the point. The point is, this is a tool to. I mean, I think the water-cooled stuff is really, really good. Don't take that the wrong way. But there's no kind of hidden agenda for this tool. It is what it is. It's going to calculate out using the same types of parameters for both systems. So this would be kind of the final analysis. And again, if someone wanted to take this and then apply it in some other fashion and some other kind of cost accounting or analysis, they could. There's no problem with that. Just to wrap up, I mean, there's a couple other things that we're working on, is being able to do multiple options. So like right now, you go boom 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 through all these spreadsheets, and you get an answer. And then if you want to compare it to something else, you go back and you get an answer. So we're just, that to have that ability to compare different outcomes is really, an important part of energy modeling, certainly, to be able to compare those. So that's really it. I'm glad people got on. I think this is something that's very important. I personally think that as computers, as servers become more and more dense, we're going to need to look at an alternative to full, there'll always be some level of air cooling. I don't think it's going to go away completely, but especially for servers or clusters that are very high density, like in a supercomputing, there's really no other way except to use some type of liquid cooling. So I'm a big proponent of it, but I'm hoping that this tool will help, drive those decisions or help make those decisions, and in the future, with further releases and more functionality, it'll get even better. So, okay, that's all I have. Valerie, you want to look at some, do we have time for questions?
I think so. Let me check with Mary. How are we on time for questions, Mary?
We have another 10 minutes. If anyone has any questions, please feel free to leave them in the comment box below.
I did see one in the Q&A already, Bill, and perhaps you can address this one.
Sure.
Randall asked, is the calculator valid for both new data centers as well as retrofits?
Yes, it is, and this gets into this part of when we're looking at, if I start with the existing data center, what's always tricky is applying a new system to a data center and trying to calculate the energy and the space requirements without tying it to the existing building. So the building is already there, but realistically, if you're putting this in, you're occupying space, you're taking a space of the building, realistically, you need to count that square footage in. So on the new building side, since that functionality is already built in, you can lay out, you could just tell what size the data center, or tell what the size the load is and those parameters, and it's applicable to a new data center as well. And as we get some more functionality in terms of the different mechanical systems, that'll get more robust, I'll use that word, in the future, to be able to model different systems. So the answer is yes, it definitely is.
Okay, good. Another question in the technical side of things from Bob, and I'm not sure it applies to this tool as such, but I'll let you take a look at it anyway, is what happens to the water after it goes through the server? Is it thrown away with that additional heat, and do we end up with more significant water usage? So maybe you can speak a little bit to
sure.
that.
It's a good question because, you know, way back when, and actually in still some municipalities, we would have like what was called once through cooling. So like I live in Chicago, the river runs right through the financial district. So, you know, 20 years ago, you would see, you know, craw units or crack units that would use water, and they would run it through the compressor, and then, like you're suggesting, they dump it right back into the river. So, or, you know, other systems like that. Now, in this case, it's a closed system. So other than, you know, makeup water for when we're, you know, cleaning the cooling tower or whatever, or, you know, through evaporation, there's a minimal amount of makeup water that's required because it is a closed loop, and we're not discharging the water that's been used to cool the servers. It's a good question, though.
Okay, good. Then not so much on the technical, but on availability, is will the calculator be available for all users? And is there a charge for its use? I can address that a little bit. There's not a charge per use because it's not an online tool. This version, at least, the first version, is download. And you can download that from, and I will put this in the chat here so everyone can see it. This is the link to download the tool. It is free to members of the Green Grid. There is a $150 charge for non-members, but I'll take this opportunity to remind everybody that the Green Grid does have individual memberships available. There's a bit more than the $150 for this tool, but it will get you access to all of the tools and white papers and things that are in the library. So here is a link for how to join the Green Grid, or at least look into an individual membership if you don't want to pay the $150 for the tools. Speaking of those other tools that are available, I think then question, Bill, maybe you can address this. There are several tools that are out there. Of course, TGG is probably best known for the PUE that was originally kind of launched us as a name in the industry. But since then, there are multiple other tools, including free air cooling tools, and most recently, the performance indicator tool. So how does this tool kind of fit in with that package of tools that the Green Grid has created?
Sure. It's, you know, this particular tool as it stands now is really kind of has a singular focus on overall costs and operating costs, where you know, some of the other tools within the Green Grid's you know, package of different tools are more focused on either energy or greenhouse gas or something like that. So there's not a hard connection between this and those, but the same, you know, the same kind of principles apply. I mean, I could see at some point where, you know, maybe there's a bigger suite of tools. I don't know this for sure. I'm speculating where something like this might fit into it. But right now, it's really kind of a standalone tool that, you know, certainly you can go back into, say, calculate the PUE or other aspects of it. That's absolutely possible. It's just there's not a kind of like a hard-coded connection.
So yeah, it doesn't replace or cross over in other ways with those other tools. It's a new tool in the toolbox. Okay, let's see. Do we have any other questions? Here's one more. Regarding how PUE eventually became a standard, do we see this becoming a requirement, or is this a tool better suited for internal use?
I mean, certainly for right now, this is just a tool for decision making. I mean, I can't really speculate if, you know, at some point in the future, if, you know, there might be kind of baked into some, you know, ASHRAE standard or whatever based on certain power density or whatever you need to use a water cooling. I don't know anything about that, nor do I anticipate it. So for right now, it's a helpful decision making tool, and it allows for kind of looking at the life cycle costs of it. But this is a good question, because ASHRAE also requires on the facility side different types of economizers and such. You know, maybe there's a point in the future where this becomes such a huge, or continues to become such a huge power user, that there's some dialogue on how that's cooled. So it's another interesting question. Valerie, I also have another question here. This person, it sounds like it's some experience in this. They have, you know, a very warm water that can be reused for other things. You know, like I've done analysis on using it for, like, you know, snow melting systems, or you know, heating, cooling chillers, a lot of different applications. So his question is, will the calculator be able to include reusable energy? No, it doesn't right now, but that is a fantastic idea, because especially as we're going to the much higher water temperature, there's definitely a reuse for, preheating, boiler, makeup preheat, and such. So this is good. You sent me some ideas: heating pools, floor heating, industrial. So absolutely, as this becomes, and it will be, I truly believe it will become much more of a norm, and the temperatures will become much warmer because of the energy considerations. We're going to have the ability to reuse a lot of that energy that's, you know, built into that water for other things. So it's great. Thank you.
Did have a question about whether when will the calculator be available for public use. There are no plans at this time. I don't have a date to give you. Like I said, it is available for public download with purchase at this time. Let's see. Same thing goes with the trial. I did see another question here. How to calculate TCO in case I'm using air cooling for low power processors and I want to switch to liquid cooling for high power processors. So I guess the question here, Bill, is does what you're looking at here kind of encompass that? Does that tool take in those cases?
Yes, it does. I mean, I'm assuming when we go to the high power processors, that would be a liquid cooling case. But so the way it's done is first start by modeling. You know, you could zero out the water cool equipment side and run the analysis using just air-cooled equipment at whatever temperature you're running the supply at, and then you know, you can get that TCO and then put in, go back and basically do the opposite. You know, zero out the air-cooled and put in the water-cooled at whatever temperature again, and then run that TCO. So yeah, in that case, you can run different strategies on, and especially in a new configuration where your data center might be theoretically could be smaller depending on the type of and the density of the system. You can run that and come up with the overall TCO for each one of those options. So again, yes, it can be done.
Okay. This is an interesting question here. So in a comparison, would a new data center with 100% liquid cooling require 3 times the amount of space? From my point, I'm assuming, Bill, that would depend a little bit on the type of liquid cooling employed. Is that right?
Yeah, I mean, there's a couple aspects to that. You know, if you say that there's a 1-to-1 correlation, just on the data center space, if there's a 1-to-1 correlation that the server for the air-cooled will be the exact same power and size as the water-cooled, there'll be no difference in the data center size. So like if we said if we use water cooling, we can run much higher densities and we can reduce the size of the data center pretty significantly. So, like you're saying, Valerie, it makes a difference on what the assumptions are. So you could reduce the data center size significantly. Now on the infrastructure size, it's the same idea. If we're running, you know, really warm temperatures, we might have just a small chiller or small condensing unit or whatever to temper the water in case it gets really warm out. Otherwise, we're using heat rejection device 100% without any chillers. So there, you know, you've basically taken out, you know, either outside or inside the, you know, chillers and the associated pumps. That can reduce it significantly as well. So it depends, but I would say in general, the water cooled application is gonna be smaller than for sure smaller than the air cooled, unless there's, you know, something I'm not understanding about that.
That's interesting because the question originally made it sound like the questioner believes that liquid cooling would take 3 times as much space, and what it would actually probably take less space.
Yeah. So there's some further question on depending on, okay, so there's specific cases for everything, but in general, if we're using the one thing that we will have in liquid cooling, depending on the manufacturer, is we're gonna have some kind of cooling distribution unit for sure. So that's going to take up space that wouldn't be there normally for the air cooled, but if you have an air cooled data center with CRAW units in the data center, it's still going to be less space. So it depends. I believe that there will more often the case will be to use less space for water cooled, but you know, maybe there are some that do. So it's a good question. I can't answer it based on, you know, the information. So.
Okay. I think we've got time for one more. And let's see. There's a question regarding, was there something in this tool for energy usage pertaining to a cooling tower?
Yes. So the way that the tool works, the 4 areas are the compressor, which is really the, you know, whether if it's a DX or a chiller, whatever the compressor power is, the fan power, which again will be the CRAW units or the air handling units or whatever the fan, you know, what's the source of the fan power, pumping, and that could be, you know, chilled water and or condenser water pumping. And then the final is the heat rejection device, so that would be cooling tower, you know, dry cooler. It can be any number of things. Right now, it's kind of hardwired for a cooling tower, just from a energy standpoint. But yeah, that's definitely included.
Okay. Mary, do we still have a few minutes, or do we need to wrap this up?
I think we have a couple of minutes. If anyone else has anything else.
I just noticed that a couple of questions have come into the chat instead of the questions area, so I thought we might take a look at those.
Yeah, some of the ones I answered, but yeah, I'll look too. There might be some others.
Oh, okay, good. You already answered that one. This does not. I'm not sure of the question. It doesn't come across as a question. It's a statement. The model used 22 SF per rack, whereas liquid cooling is 79 per rack. This does not consider server performance. I think it is because what you said about this is more focused on cost than on efficiency.
Yeah. This is an area again that would be nice to have built in, where it's you're right, because once we get once we start doing liquid cooling, generally, the computers, the servers, the processors, GPUs are going to run. They're going to run cooler. They're going to run faster. They're going to run better. So you get a higher performance out of the computer. So, I'm not an IT person, but theoretically, if you got 20% running better, you might say, well, I have 20% less servers. I don't know if that's true or not, but absolutely there is a performance increase when we're using liquid cooling. No doubt, no doubt.
Okay. And then how to calculate total facility size. What is the base of calculation about power system configuration?
Yeah.
So this is not a design tool as such as much as a comparison tool?
Yeah, so right, exactly. So the idea is based on, and these are all things that are kind of behind the scenes hardwired that can be brought out into the front and give the user the ability to change. So right now, the way it's set up is based on the size of the data center and assuming, some mid-level, tier 2 like facility, estimating that the infrastructure space will be, making up a number, 2 times the data center size, and then we have some additional office and kind of admin space. That's how it's calculated. So it starts out with the data center, which is more scientifically calculated based on square foot per cabinet, et cetera, and then it goes outward from there and estimates the rest of the building. Now, in other tools we've developed, we can put in the tier level, the system, the tier level meaning, whether there's like a 2N or 2N plus 1, or, how that system is laid out both on the mechanical and the electrical, and then we can estimate the size of that. So that would be a much more refined approach to this, but for what we're trying to do here, to keep it simple, we're just using multipliers of the data center size. Great question.
Okay. I think that about wraps it up. Did we talk about looking at liquid cooling technologies like immersion in the future? In general, I mean, the Green Grid, especially the liquid cooling group, is spinning off new development all the time that looks at a lot of different aspects of liquid cooling. So as far as the Green Grid goes, looking at various aspects of liquid cooling technology, including immersion, is something in the Green Grid's development future. I guess the question for you, Bill, would be, is this something you would consider being in section 2.0, if you will, version 2.0 of this tool?
Yeah, absolutely. The immersion cooling.
Good. Hope all's going well for you.
Somebody needs to go on mute. Hello, who's speaking? Okay, good. I wanted to listen in. No, just kidding. No, so yeah, immersion cooling is, when you think about it, it's another form of what we're showing here. Now, from an installation and a physical standpoint, it's radically different. But from a thermodynamic energy kind of thing, it's the same thing. I mean, we're looking at rejecting heat to a liquid medium and then taking that heat and rejecting it outside. I mean, I don't want to simplify it. There's other things involved, but the point is, yes, there's no reason other than time and resources that it's not in this version. There's no overt reason that it's not in this version.
Okay. Well, I think that's it. Any last-minute questions, type quick into that Q&A area. Otherwise, I'd just like to thank Bill and frankly, the whole team that did the development on this total cost of ownership calculator for the liquid-cooled data center. Really wonderful work, and I think this is going to be an excellent tool for the industry.
Yes.
So thank you very much, and thanks all of you for attending and giving your thoughtful questions. I hope you'll take advantage of downloading the tool, and that you'll take advantage of joining the Green Grid in doing development of the second version of this tool and all the other projects we have underway.
Okay. Thank you.
Thank you very much.